All right. Hello, everyone. Can you hear me? Is this working? Great. Right. So I would like to talk to you about estimating the carbon footprint of personal computing. Let's get started. A brief introduction. I'm a graduate student at ETH Zurich, and I'm strongly interested in research on computer architecture and operating systems. So this talk is a bit biased towards these topics. Please interrupt me if there's anything unclear. Right. Here's a quick outline of the talk. First, we'll quickly go through some background information. Then we would like to delve into the problem, the goal of this talk, and a survey of relevant work. Finally, we discuss the system design and the end product that we have. And we conclude towards the end. Let's delve into the background. This is, maybe I'm preaching to the choir, but just the basics. Carbon footprint of any application can be estimated as the energy consumption of that application and the composition of the energy that you use to run it. What do I mean by energy consumption? Energy consumption is defined as the power of the system times the latency of the application. Composition, on the other hand, depends on multiple factors. The power that is coming in through this wire depends on geography, availability, cost, and it varies for each region. For this talk, we will focus on energy consumption. There's a lot of work on composition, and there has been great talks at this conference so far. Let's dive into consumption. Energy consumption, as we just saw, is defined as power times the latency. Power dissipation is determined by the hardware. This device has a different power as compared to the device in your pocket. For instance, CPUs can have power dissipation ranging from 55 to 150 watts. A GPU might be 50 to 300 watts. The second component in this equation is the latency. And that is determined both by the hardware and the software. What do we mean by hardware and software? If you run an application on, let's say, a cutting-edge server-class CPU, it would have a lower latency as compared to an edge device. Typically, programmers care about latency. And why do they care about latency? Because there's this very famous adage. You can only improve what you can measure. Because the programmers can measure latency via CPU clock cycles, they typically tend to optimize for latency. And it's a significant factor in the user experience as well. And because energy consumption information is simply not measurable, people don't know how to optimize it. And that is the problem that I'm trying to solve. Let's dive deeper into the problem. Now, why is this information not available, especially on Linux? We're talking in the context of Linux. Let's take a look at the survey of the state. Windows supports kernel-based tracing of power information. This is a product known as Windows Energy Estimation Engine, and it is running all the time in all of your laptops, tracking power consumption for each process in the system. macOS supports kernel-based tracing. We will quickly see an example of where this information is visible. Android, as well as iOS, both support kernel-based tracing. So where's the solution for Linux? If anyone knows, I would love to know more. But from what I understand, there's no reliable solution for Linux so far. All right, there's no solution. But where's the problem? Why do people care about software-based attribution? Why should I care about knowing what is the power consumption? Well, because consumers wish they had an infinite battery capacity. All of us wish that we charge this device once in a lifetime, and then it runs forever. Like, we love to see the 100 number at the top. But that's not the case, right? It's not the case because battery capacity is restricted. Fundamentally, the charge of a battery is restricted, and this is a fundamental restriction in technology. It determines your design for, let's say, VR headsets, for laptops, and we need to optimize for it. Since this is a restricted resource, where does this resource go? Where does battery power go? Now, this slide displays a pie chart for a server-class system from Google's data centers. This server-class system is optimized for utilization. So these systems typically run at 100% utilization. They try to maximize the efficiency because for them, efficiency is very critical to profitability. And we can see the CPU is responsible for 61% of the power consumption. The memory is responsible for approximately 18%. And this is for a system running at peak efficiency, right? This is a consumer class system. A consumer grade system almost never runs at peak efficiency. None of us push our systems to the peak. So in this system, these numbers are much, much lower. And because these numbers are much lower, I cannot say, people typically say, oh, your power is determined by the CPU. That is not the case. There are many other components that are quietly chipping away at your battery, and we don't know about them. And I would love to expose this information via this project. So given all of this problem, let's quantify and substantiate our goals. The goal is to develop a framework to reliably estimate the energy consumption of any process running on a Linux system. I want to build the system, and I want to expose this information to the programmers as well as the users. We want to report these statistics to end users for an easy-to-understand format, and to the developers via APIs that improve the actionability, right? We want the programmers to take action on this information. Great. We understand what is the problem. We understand what we're trying to build. Let's try to see how others have done it so we can do it better. This is the slide that I was talking about earlier. You can see the Windows Energy Estimation Engine. I'm guessing most of you have seen this screen, right? It reports to you how much battery was used by each of these processes. How does Windows get this information? It's an absolutely beautiful system. I have reverse engineered a lot of it, and I can discuss more details about it. But unfortunately, due to the short time, I have to skip those details. If you're interested, please let me know. One more data point. This information is also available in the task manager. If you take a look at these two columns, you can see a short-term power impact as well as the long-term power impact of a process on your system. Let's dive into macOS. Windows gives you power estimate. macOS gives you energy impact. Energy impact is a relative number for each process. So you can see here that in a short term, Firefox has a higher impact as compared to Chrome. And in the long term, it has a much higher impact. So this number does not mean joules. OK, this number has no unit. It simply quantifies what is the relative impact of this particular process on your entire system, on the entire load. Let's switch some gears to mobile devices. We take a look at Android. Android also tracks this information. You can see here these different devices as well as processes are consuming, let's say, 56% of your battery since the full charge. Great. I mean, it's beautiful information, but why don't we have it for Linux? I don't know. And that's something that I would like to solve. Right. How many of you are aware of this application called PowerTOP? Has anyone heard of it? OK, then my presentation is quite strong. Right. PowerTOP is an application that was released by Intel approximately a decade ago. PowerTOP informs you about the power estimate on the left side, this power estimate for a process, a device, an interrupt. So you can theoretically estimate the power consumption of a process on Linux. Problem solved. Why are we sitting here? Because I don't believe this is the solution. I believe that PowerTOP has significant problems. My first rebuttal for this is that power estimate is a discrete event. Power is measured at a particular point in time. I believe energy is a much more fundamental data point. Energy can be significantly more correlated with the battery drain. We care about energy consumption much more than power estimate. Second, PowerTOP is extremely vendor specific. They use a lot of, let's say, CPU tricks to get the information that they do. It does not run well on other vendors. Third, what is the actionability of this data? OK, you know that process X consumes 1.45 watts. How do I, as a programmer, optimize it? Why do I care about this? So what is the use of this data for our target consumers, for our end users, and for programmers? We don't know. Right. So I believe that PowerTOP is not the solution. And I would like to propose a much more reliable and useful solution. OK, now let's dive into the system design for the solution. This is a very high-level overview of the system that I've been working on. There are two inputs to the system, a multivariate regression model and one output. The first input is device-specific measurements. If you remember from the background, we talked about power is determined by the hardware. These device-specific measurements come from the hardware. The second input is the runtime, the latency for the processes. This information is already available as part of the kernel process accounting infrastructure. We need to extend that infrastructure to make it much more useful, but a significant fraction of it is already there. Finally, we input both of these data points into our model, and then the model outputs the energy consumption for each process. Right, so how do we get the device-specific measurements? The goal here is to determine the regression parameters. You have a regression model. The model has some parameters that you train, and then some inputs that you give during the runtime. So we want to determine the parameters during training. The method for this would be quite simple, in fact. It's quite similar to ablative studies that are used by many papers before. What we do is, maybe I would like to simplify this. I can see, right, so let's try to make it more interesting. Imagine that you have a huge water tank, OK, a 1,000-liter water tank with a single input and 1,000 outputs. So you have a lot of small pipes going out and a single big fat pipe coming in. My question to you is, how do you determine what is the drain rate or what is the output rate for each of the small pipes? You're not allowed to measure it directly, but you have to estimate it. That is a very good analogy for the problem that we're trying to solve. So if you think about it, a solution immediately clicks to your mind. You close all the pipes. You isolate the amount of water in the tank, and then you measure it. Let's say at the beginning it is 1,000 liters. Great. Now you turn on one pipe, not 1,000, just one. You turn it on for 5 seconds, and then you close it again. And then you measure the amount of water left in the tank. Earlier it was 1,000. Now it is 995. And you turn on this pipe for 5 seconds. So essentially, you've just measured the drain rate as 1 liter per second. And you do this repeatedly for all the pipes. So you have 1,000 pipes, and you repeat this process 1,000 times. And that allows you to determine the drain for each pipe in the system without ever directly measuring it. We're doing something quite similar here. We have 1,000 devices in this system running simultaneously. All of them have a single input, the battery. None of them give me the information that I need. OK? This information is simply not available, neither in data sheets nor in the system. So how do we solve this? We turn off everything. We measure the static rate, and then we turn on them one by one. By turning them on one by one, I can understand, let's say, that this screen is probably dissipating 5 milliwatts. The CPU is probably taking up 20 watts. We repeat this process across all the devices that are accessible, and we sweep them. So this gives us the parameters for the multivariate model. Right, let's quickly take a look at the overview. So we now understand how to get the device-specific measurements. Let's go into the process accounting infrastructure. These are the inputs at the runtime. Right, so how do we determine these inputs? Well, to some extent, this information is already available. You have the CPU slices accounted for each process. The kernel tracks how much time slice has been already allocated to a process. It also tracks which cores the process has been allocated to. This information is used by the scheduler. It also tracks what is the resident memory information, the file handles, the network connections, sockets. So a large chunk of this information is already available. All we have to do is simply pull it into our model, give it as input to the model, and get the output. For each running process, we poll this infrastructure. If you guys are familiar with /proc/ the interface /proc in Linux, that is exactly the interface that we poll. Once we poll this, we input these values into the regression model and try to estimate what is the energy consumption. So we have the power coming from the hardware and the latency coming from the infrastructure. And that gives you the energy estimate. OK, all said and done. Let's talk about the final product. What are we delivering here? This is a mock-up for a product that I've been working on for a long time. You can see here, we try to track the battery level across time. And we report to the user, OK, let's say your screen is draining a lot of power. You should probably try to reduce your brightness. Your Bluetooth is, OK, not so bad. Inkscape is a good consumer. This is what end users care about. This is what they can use. This is what they can understand. Let me give an example of how this graph would be useful to you. Let's say you have a presentation to deliver tomorrow. You've not prepared it. And you want to make it today. You want your laptop to run for like 10 hours constantly, right? How do you make it? How do you extend the battery life of your laptop? You would close the applications which are killing the battery, right? But do you know that right now? You don't know that right now. This information will be available that will enable you to do this. OK? It improves your productivity. It improves your usability of the device that you've paid for. This is for the end users. Let's take a look at the programmer side of things. For the programmers, we would like to upstream this kernel module, the changes to the accounting infrastructure, and expose a reliable API. One example use case can be that as you're programming, you include this information in the IDE. So the programmer can immediately see what is the impact of, let's say, some design decisions in the software at the program time. This significantly reduces the feedback loop, right? So we want fast feedback loops to enable programmers to optimize energy much more efficiently. Right. That was the product. And now we would like to conclude. I believe a very, very useful feature is missing from the Linux kernel. Our friends, other kernels, have already included this information. They're already working on it. They're optimizing it. But we don't have it. And we need to get it. I believe this model will empower both our end users and programmers and enable them to calculate realistic carbon footprint of their products, of their applications. We care about carbon footprints, right? And the first step towards that is to get the energy consumptions. And that brings me to an end. Thank you very much. Any questions? Yeah.
Is it possible to challenge the hardware device measurement you are trying to study from a software perspective, by a hardware perspective, from something like a power meter,
yeah.
Plugged
yeah.
from the micro components?
Yeah.
Is it possible to compare that?
That's a great question. That is, let's say, the traditional approach. You poll the power consumption via.
I'm speaking about the hardware.
Yes.
Wi-Fi,
yes.
Bluetooth,
exactly.
Keyboard, backlights, things like
yes. That is how typically you would do it. But we are talking about a scale of like billion devices. This is in the kernel, and it will be deployed across billions of devices. I cannot go and plug a multimeter into a billion devices.
My question was not to assess all the kind of hardware we have on the
Yes.
but more to see if your estimation
Yes.
from a software perspective
Okay.
are completely correct.
You're talking about verification. Yes, we would need to do that. That is, yeah, definitely. I agree with you. Yes, we would need to do that initially. We need to verify if the model is indeed getting the correct values. And yes, from the software, you cannot see it exactly. We definitely need the exact values to validate the model in order to make it more accurate. I agree to that. Yeah, that's a great point. Thanks. Yes?
My question is that does your tool generate any, let's say, additional overhead on energy consumption, like in desktop?
That's a brilliant question. That's an absolutely brilliant question. Now, if you think about it, we're doing machine learning here. Okay? This is a multivariate regression model. When people say machine learning, why don't you say neural networks? Or why don't you say some large model? Because of the load. We want to minimize the load on the system while this is running, because this is going to induce a constant load on your system. to minimize that load is the reason why we picked a multivariate regression model. It will induce some load, and we can reduce it via two ways. One, you optimize this model, and two, you increase the frequency. So instead of running it at every 5 milliseconds, you would run it at, let's say, 20 milliseconds. Does that answer your question?
Why you increase the frequency can reduce the energy consumption?
So whenever this module runs, it wakes up the processor, and then the processor has to do something.
Yes.
And because the processor is doing something, there's a spike in the power consumption of the system. The C states, if you're aware of the C states, they switch from C3 to C7, and your power goes up. So we want to minimize the load.
Okay. As far as I know, is that if you increase, like, I think you mean the CPU frequency, right?
Yes.
So if you increase the CPU's frequency, maybe the instant power consumption will be higher, but you can finish your job earlier, so that
Yes.
the energy consumption is lower.
Yes,
right?
but we are running this every 5 milliseconds. So your CPU cannot sleep. So right now I'm not doing anything. This system will go to sleep in 3 minutes. OK? But what if this thing is running in the background? It will not allow the system to sleep. Does that?
You does not allow it to sleep, so it will constantly consume energy.
Yes, and that is the load. That is the load that we want to minimize. So you increase the frequency to reduce that.
Okay, I see.
Yeah. But that's a great question, yes. Thanks. Right. Yeah, please.
I want to throw some questions now. Two questions are, I heard about something like Power API.
Yes.
Do you know this?
Is that from Jack Dongara?
I just know the name of the API, which sounds like something helps you to know the consumption,
OK.
energy, during the runtime.
OK.
So my question was,
Right.
what is the difference between Power API and what you are aiming? Maybe it's not a kernel module, as far as I know.
OK.
So maybe the difference, the big difference is this one, but maybe not. I'm not sure about that. You know Power API?
I am not familiar with it, but I will take a look at it.
Okay.
Thank you for bringing it to my notice. Sorry.
And in Ria product, and you have also scaffold. Do you use scaffold? It's about the same thing as Power API. It measures the consumption per process via Docker.
Via Docker.
Yes.
OK. What's the name?
Based Power API.
Yes.
And scaffold.
OK. I'm not familiar with them. I'm familiar with Intel RPL. Yeah. So.
But I will give you contact to maybe research contact on this kind of thing because you work on side subject. So
Thank you.
Contact. And the other question was
Yes.
about the name of your product. Just a challenge. It's realistic carbon footprint, but you begin your presentation by
Yes.
saying we have here the consumption of energy.
Yes.
This is the focus. But you of course know that carbon in IT
Yes.
is not only a thing of consumption.
Yes.
It's also conception.
Yeah.
Hardware conception.
Yeah.
It depends on the country, but here in France we have
Yes.
this carbon footprint.
Yeah.
Three power system. So you have something like 80% of the carbon footprint
Yes.
by building this device, and
Yeah.
maybe 20% or 15% by using this device. So the name of your product is maybe usage.
OK.
You see what I mean? It's just a challenge more than a question.
Thank you. I appreciate that. Yes. I do understand the 80% 80-20 ratio, and
In this country, as you said.
yes, yes. But I do believe that this is a fundamental. It would be something very useful for end users and for programmers. Yes. And we can. I saw some projects which expose the composition. So let's say you detect in which country the device is, and then you can multiply it by the factor of renewables, factor of fossil fuels to estimate the carbon footprint.
As a client of cloud solution,
Yes.
we do really care about what we call the location base.
Yes.
We really would like Azure or Amazon AWS
Yes.
to tell us where the server is running.
Yes.
extrapolation, and maybe they are doing well, but maybe not.
Yeah.
Well, really we need to know that.
I think AWS exposes this.
Okay.
AWS has some metrics in the dashboard which give you this information, but I'm not an expert in
And
AWS.
this is where your product is very significant.
Yes.
Because thanks to this kind of thing,
Yes.
Amazon, Azure, and etc. adopt this kind of thing.
Yes.
Based on Linux solution, of course.
Yeah.
It will change the customer point of view in managing the energy production.
That is the end goal. Thank you. I appreciate that. Right. Any more questions? Great. Thank you very much. And it was wonderful to talk to you about this project. I hope you have a great day.
Thank you.
Right. Okay. Yeah. Let the people go. Yes. We have 10 minutes. Hey, let me turn it off.